Okay, so let's talk about motion. We know that motion is just things that move. In physics, we use a couple of different vocabulary words that we're probably going to mean something different now. The first one is mechanics. So mechanics is just the study of how stuff moves. I'm going to take an object and I'm going to study what made it move, how it's moving, and that term is just called mechanics. And we use another term called kinematics to describe the motion that the object's doing, and we use different things like words. So, for example, we could say the car crashed into another car, and that would describe the motion. We can also use diagrams saying car 1 crashed into car 2. And maybe we could say this person probably isn't feeling so good. So that would be like a diagram example. We could use numbers, and we could say car number 1 had a certain weight, maybe like 5,000 kilograms, and it interacted with car number 2 that had a weight of 3,000 kilograms, and maybe we could do some calculations about that. Another way to do it is with graphs, and we could say at a certain point, let's change colors, whoops, oh well, so car 1 was moving along in this direction, and maybe at another certain point, car 2 is moving in this direction, and where the points intersect, that's where the crash happened. And so we could show that on a graph. And another way we could do a description of motion is force equals mass times acceleration, and we could describe it by calculating how much force this car exerted on the next car. So that's kind of what motion is talking about. So this car is doing a motion, and it is making a crazy motion. So how would we describe it? Well, a proper description would be really detailed, not just saying that car's crazy, that car's out of control, it's leaping through the hills. You would try to write an actual statement that's going to help you make sense of it. So maybe in this point you would say the car is moving fast off-road. It's not on the freeway anymore. It went up a hill, went airborne, then crashed down the hill, and continued up the next hill. So maybe you could write something like that. Something that's going to put the visual in, that's really descriptive. So when we are talking about things, the system is the part of the universe we're choosing to study the motion of. So we don't want to look at the whole world in this case. In this case, we just want to look at the car. The car is the system that's moving that we want to study in this case. Maybe it's going to be a ball rolling or a rocket shooting into space, but whatever's moving and what we're studying, we just want to zoom into that. So in this case, it's the car. And then the next part says to draw a model of the motion. So that car's going up and down and up and down. So I might want to like draw some arrows like going up and then going down. And it's going back up and it's going back down. And that will kind of show me a model of what the motion of that car is doing. So it kind of makes some sense. All right, so there's two ways we can describe motion. The first way is scalar, which is just a number value alone, but it still has units. So that could be like seconds or kilometers or some kind of number. So like 60 hours. That is a scalar number. It has a magnitude of some sort. Vector is the same number with a direction. So maybe I went for 3 seconds in the southeast direction. So that would make this a vector quantity. Maybe I was moving 3 meters per second at the velocity, moving in a southeast direction. So the car moving 25 kilometers an hour, that would be an example of a scalar quantity because there's no direction. But this one moving 25 kilometers per hour to the east, that's a vector quantity because it has a direction associated with it. And in physics, we're going to need to know the difference between those two, and we'll have to study it out. Two more words we need to know are distance and displacement. So distance is how much ground an object covered during its entire motion, and it doesn't have a direction. It's a scalar quantity. Displacement does have a direction, so we call that one a vector quantity. So if we look at Miss Miceli here running around and we look at her movement, she went 4 meters to the right, then she went 2 meters down, 4 meters to the left, and 2 meters back up. So her total distance was 4 meters plus 2 meters plus 4 meters plus 2 meters. So the whole thing added up was 12 meters. No direction, just a distance. But displacement is a little different. It's the overall change. And in physics, we make a triangle. That equals the change. And to figure out the change, it's the final value subtracted from the initial value, and that equals the change. So for this one, displacement, we usually refer to x as some kind of distance quantity or displacement quantity. That's kind of the variable we use. Sometimes it's d in meters. So now if we look at this, if we look at this movement and look at the displacement of the movement, I start here, I make this lap, and I end here. I end in the very same spot that I started. So my final position is equal to my initial position. So my overall change after I did all this is absolutely nothing. So this overall change here for this problem is 0 meters. Nothing happened. 0 meters. Okay, let's do another example. So here we're looking at a skier, and they want to know first what's the displacement. So remember, displacement is final minus the initial. So final is d right here, and we can see it's here, and initial is right here. So all we need to know is this entire distance. They went all over the place, but they started here, they ended here. So 140, because it's 100 here and 40 here. So the final position is 140 meters minus the initial, which was 0 meters. So our displacement is 140 meters. Now the distance is another story because this skier went all over the place, and we need to track all the little segments of the movement. So for that one, I kind of like to organize it. So I'm going to go from the distance from A to B, and then B to C, and then C to D. So from A to B is from way over here all the way over there. So it's the 40, the 100, and the 40. So that first leg is 180 meters. And then the second stretch, they went from way over here to way over here. And that is a stretch of 140 meters. And then they went from stretch C to stretch D. So from here to here, and that's another 100 meters. Now remember, this is distance, so direction doesn't matter. So now I add all this up, and I should get 420 meters for the total distance that skier went. So interestingly, after all they did, they really only made a displacement of 140 meters, but it took them 420 meters to accomplish it. All right, same idea. Now we have a guy on a football field. What's the displacement? So for displacement, it's the final, which is D. And remember, this is -5 yards here. And initial, which will be here. So what's the difference between 50 yards to -5 yards? Well, if you can't figure it out in your head, you can do it this way. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55. And it's not meters this time because now it's yards. So we would put yards. Now for distance, we got to do all the segments again. So A to B, B to C, and C to D. So A to B is 50 to the 15. So 5, 10, 15, 20, 25, 30, 35 yards. And then between B and C, we got 5, 10, 15, 20. And then C to D, we have 5, 10, 15, 20, 25, 30, 35, 40. So that distance is all that added up, which is 95 yards. And we got it. So 2 more vocabulary words, speed and velocity. So speed, we're pretty familiar with, like going maybe 60 miles an hour, right? Or 65 kilometers per hour. Or, I don't know, 10 meters per second. So that's just telling us how fast we're moving. So these are some examples. And then velocity is the same thing. It's the speed, but with the direction. So it's telling us what way it's going. And sometimes we use positive and negative numbers to show the difference in the direction that something's moving with velocity. In physics, we're going to always convert things to meters per second because all of the equations that we're going to get into are based on standard units. And the standard unit for speed and velocity is meters per second. So that's why we needed to know how to convert from metric to this. So we would have to know how to make 65 kilometers per hour meters per second. And that's why we started practicing that. So for speed, it's however far you traveled, x is the distance, divided by how long it took you to get there. So x is in meters and time is measured in seconds. So that's where we get this unit from. And then velocity is, oh, here's a triangle. What does that mean again? The change in your position or the displacement means the same thing. So how much did your x change divided by how long it took you to do that, which is time. So this is in seconds, this is a unit of time, and this will be in meters. So it'll still be in meters per second, but it's going to give us some kind of direction too. And usually that'll give us a positive or a negative sign to tell us which direction. We'll get to that a little bit more as we go on. So just to practice, this is all worked out for you just to have an example ready to go. So let's change colors so we can see it. So Lisa took a trip. She traveled 440 miles and it took her 8 hours. What was her average speed? So this is our formula. Speed is equal to the distance divided by the time. So 440 miles and it took 8 hours, and that's going to give us the speed of 55 miles per hour. So remember, speed is always going to be a distance over a time. Miles is a distance, hours is a time. So that makes sense. So all of these problems are going to have a component of making sense, and make sure your units match each other and make sense. Okay, so the last thing you need to do is go to this little interactive website, do the interactive, and then when you're done with it, just put a little screenshot up there. I think I called it a quiz, but it's really just a little exercise to run through. So post it here in your slides, and then you'll be done with this segment. Come to office hours if you have questions, 1 o'clock to 2 o'clock on Tuesdays and Thursdays. All right, sounds good.